It is when this thing is equal to 0 or pi, right? So it is equal to 2 pi over lambda, x is equal to pi, correct? Or x is equal to lambda by 2. Am I correct? Okay. Now, there is an important thing about standing wave. If this is 0, because the electric field must be 0 on the surface of the perfect conductor, right? So it goes up like this, comes down like this, go up like this, come down like this. I mean, don't laugh at my drawing, my drawing is like that. Okay. Now, so at this point is lambda by 2. Okay, you got it right? Agree, huh? Lambda by 2, right? Hey, but have you ever asked? Have you ever asked that? Okay, if my wave, isn't it from here to here is equal to lambda? From here to here is equal to lambda. This is wavelength, right? Minimum to minimum is lambda, maximum is lambda. But 1 by minimum to minimum is lambda by 2. If a wave minimum to minimum is wavelength 1 lambda, maximum to maximum is 1 wavelength lambda, but now my minimum to minimum is 1 lambda, is lambda by 2. Sorry?
Lambda is based on time and lambda by 2 is based on the distance.
Lambda by 2 is based on distance. No, lambda is a wavelength. Wavelength is distance. So this one no problem. Lambda by 2 is minus 1.5 meter. Why minus? Because it is counted backwards. Z is equal to 0 and backward 1 minus 1.5. But the question is why like this? Why lambda by 2? Now if you want to know this, we have to go back to these very important slides. Now, I have two vector rotating. Alright? Now, for perfect conductor, theta here is equal to pi, does not matter, minus 1, whatever it is. But you can see that even if theta equal to 0, that means how fast that this thing rotates. When a propagating wave, the phase is jj beta x. This is how fast the phase change. The phase rotate as beta x or beta z. But these reflection coefficients here, this vector, rotate as twice as fast, 2 beta z. So it rotates twice as fast. So you can see that actually this standing wave is double the frequency of the incident wave. Okay, the standing wave is double the frequency, so the wavelength is shorter. The so-called this so-called standing wave wavelength is the half of the original one, because this guy rotates twice as fast. Then you will encounter again the same thing on transmission line. The reflection coefficient along the transmission line, the phase change twice as fast. Alright? So in fact, these questions, this question, you don't need to answer this, you don't even need to go to these equations already. Because, you know, the next one is lambda by 2 away, the next one is lambda away, and so on and so forth. Then what is the maximum? What is the maximum away from the perfect conductor? Lambda by 4. Okay, this is lambda by 2. This is lambda by 4. So if the question asks, instead of asking where is the first minimum, which is lambda by 2, ask you where is the first maximum, lambda by 4. Okay, so very, very straightforward. Don't even need to use any equations. Alright, any questions? Do I need to go through again? Okay, let's do a small flavor of transmission line. Alright, we have time. We have a small flavor of transmission line. Then we don't have to rush so much. For this paper. Wrong one. Screenshot. We teach less, learn more. We don't teach anymore. Huh? Everything, every time trying to teach less, very troublesome now. Sorry? Don't know, depending on where we have enough time. Okay? Why cancel? Loading up. Open the PDF file better. Okay? Can. Okay, doesn't matter. Transmission line. Okay, transmission line. What is transmission line? Transmission line, of course, you know lah. The power frequency transmission line is your. We don't have this one. In Singapore, you don't see this one. Okay, overseas you see a lot. Singapore, all the power cables are buried underground. Okay, good and bad lah. No. Okay, transmission line. These are transmission line. These are transmission line. Okay, these are transmission line. Alright, these are also transmission line. These are transmission line. Alright, the free space is also a transmission line. Okay, free space is also a transmission line. Because transmission line means that it is a means of getting a medium, that getting energy or signal from one point to another point. Okay, so the transmission line is that you get a sending end to receiving end. Now, development of transmission line over the year, the simplest transmission line is this, 2 wire. 2 wire, okay, voltage, current in, current out. Now, but this kind of transmission line becomes bad when the frequency goes up. Why? Because you see, when you have 2 wires, what do you have? You learn from the first part. You have your electric field, you have your magnetic field. Okay? And when the frequency goes higher and higher up, the stronger are these electric field and magnetic field outside. And what is the consequences of these electric field and magnetic field outside the wire is, first of all, lost energy. These are the energy lost in space. Secondly, interfere with other people in the vicinity. Because if this thing is 50 Hz, I have another cable here. This guy is going to induce EMF down here, Faraday's law, right? So when then people progress, they say, okay, if that's the case, I use coaxial. Because coaxial, then the electric field and magnetic field are enclosed. Okay, are enclosed. Enclosed, there is no problem with this one, right? Good. Yes, enclosed. But then if enclosed, I will have a rigid copper pipe, dielectric, another rigid copper pipe inside there. Wow, that kind of transmission is shock, man. You know, you have to bend. You got rigid copper cable. So they all say, okay, in that case, how to make it non-rigid? To make it non-rigid, this one rigid become replaced by many strands of small little cable, and this outside here replaced by a mesh, wire mesh. If you have opened out a coaxial cable before, I believe you have. These are wire meshes. Now, wire meshes are good when the frequency is low. When the frequency goes up, there will be leakage through the wire meshes. Now, the efficiency of wire meshes to contain the energy within is, okay, inversely proportional to the wavelength. When the frequency go up, it's no good. Okay, wire mesh can actually block the electromagnetic wave. Is very evident, okay, in your microwave oven. Okay, on the microwave oven there is a wire mesh right there. So when you look at it, you can see whether the chicken is cooked or not. Your face will get cooked. Alright, if it does not block the microwave energy, your face get cooked when you look at the chickens already. Alright, so it's cool. But when the frequency go up, wavelength goes small, the thing starts to leak again. Okay, when the thing starts to leak again, what to do? Do you have to go back to solid? But if you go back to solid, people also think, hey, if it's solid, I can confine the energy therein. But why I waste all the money, put another dielectric, put another this one, another conductor? Why can I put an empty solid plumbing? This is become waveguide. Waveguide got rectangular, got circular. Okay, circular waveguide is basically this kind of thing without the center conductor, without the dielectric. But circular waveguide or cylindrical waveguide, the names mean, is more difficult to analyze. Okay, analyzing circular thing require better function, and that's why optical fiber is not easy to handle because it allows better function, first kind, second kind, all that. So when the rectangular waveguide is easier because we only use sine, cosine, very easy to analyze. If you come to see higher here, we'll teach you that one. Alright, so this is how this thing evolved. But of course, the involvement of this one, microstrip and all this, is because of miniaturizations. Miniaturization. You cannot put a waveguide like this inside a printed circuit just now, right? You cannot have this kind of thing here. This is your microstrip line now. Okay, this is your microstrip line. We analyze all this thing as well. Okay, we analyze using this one. Okay, and with this one, there will be all these problems. Okay, there will be all these problems, but it cannot be helped. We need to be small. Okay, we need to be small, and to this, okay, we have another way of treating this one. But as I said, we come to senior year, then we talk about it. All right, but this is a compromise that you need to be small. All right. Now, how do we handle transmission line? To have a transmission line, okay, we cut the transmission line into many small elements. Okay, just like integrations, remember, when you want to integrate this one, we cut them into small little segments, we cut them into small little segments and add them up, right? So same thing, we said transmission line, I can cut them into small little segments. Okay, and each segment got the resistance, inductance, capacitance, conductance. Each segment got a circuit like this. So it's repeated by many of the same segment. Okay? Of this one. Alright? Okay. R prime, L prime, G prime, C prime, okay? Resistance, capacitance, inductance, conductance. Now, this is order. This one you might not be unfamiliar because in this column, this coaxial, these are the values that we have determined before in our electric field and magnetic chapter. We determined all this before already. Alright? 2 wire is not alright. So when we analyze one small segment, okay, we analyze one segment. I'm going very fast because I'm going to go through again, okay, on Friday and next week. Okay, we analyze this by using very simple circuit analysis. KCL and KVL. KCL and KVL. I look at KVL here. Okay, sorry, I look at KCL here. What is the current flowing in, current flowing in? The sum of the current flowing in must be equal to 0, right? And we use KVL, what is the total loop voltage must be equal to 0. And you use KVL and KCL, okay, and we will do differentiations, okay, you will do differentiation, this part you don't need to know actually, and it ended up this equation. Hey, these two equations is very similar to your del squared E plus Ke equal to 0. K squared E equal to 0. Very similar, right? Del squared. This is del squared. This is your Laplacian squared. This one being over, isn't that equal to K squared E? So you replace V with E, the two are the same. So actually, you can see that all trends or all route is going to roll. You know, no matter how you analyze using KCLs, KVLs, you analyze using Maxwell equation, everything goes back to your Helmholtz equations, wave equations. Alright, and gamma is equal to alpha plus j beta. Isn't the same? Now, if you look at this carefully, now I write this as del squared E minus gamma squared. B equal to 0. Alright? Because this is del squared. Okay, bring it over minus, right? Correct or not? Can everybody see that this is del squared V minus gamma squared B equal to 0? Can, huh? Okay. So what does it mean? It means that K squared is equal to minus gamma squared, right? Am I correct? Okay, or gamma squared is equal to minus K squared or whatever. So what does it mean? So gamma is equal to what? Gamma is equal to what? Minus JK. If you substitute gamma equal to minus JK inside here, you see that, well, it is exactly the same equations because, you know, K is equal to, so K is equal to beta minus J alpha, gamma is equal to alpha plus J beta. So, same. So, once again, it's the same equations at the end of it. Alright? So, okay, we will stop here and we will continue. So, all the things that you learn in the transmissions, reflections, refraction coefficient, transmission coefficient, everything will be applied to transmission line. Everything that you learned previously, because they are the same equation, they have the same behavior. Alright, so we will, where is this one? I think this one. How to close this one? Okay. So, ladies and gentlemen, nice. No lah. So at least I know where do you go wrong now. How about that? And whoever didn't do well, I will chase lah.
What's the section constant? I think you just pass away, you fucked up already.
I got it.
What's this?
It's very simple. This one, I expect everybody to be 100 marks. This is a very simple one. Coefficient what?
And constant the same thing.
Same thing. Refraction coefficients, refraction constants are they are interused. video already. The one thing when you do this, when you do sit down, okay, don't always try to calculate. Don't always try to calculate this one. Press calculator, press calculator, press calculator. If you every time you press calculator like this, it's really waste of time. Okay, remember this is always equal to 125 divided by square root of epsilon r. Because this is equal to mu naught epsilon naught epsilon r. Okay, so it is always like this, and this is much faster than every time you press this one. Wow, you got so many zeta you calculate and you make. Okay, so this is a shortcut that you guys should know how to do. Okay, are we done?
It's larger, right? But the function is larger. Because you got settled one, But you must transmit this unlimited. But the median, I don't know, I use the formula, I anyhow guess. I anyhow went some of them,
Actually, don't need calculation at all. All the answers are calculation at all. Just see and then just get the answer. No need calculation at all.
this constant is this constant. Okay, done. This constant.
131哎，131哎。I put 1K1.
I never based on this day, I based on this.
Yeah, correct.
Because your total power transmitted is a few minutes. Yeah, should be the same.
They say transmitted electric field and not
But I still get more. Same thing, different thing.